All right, welcome back to part one of the Flipping of the Switch on Electric School Buses series, where we will provide an introduction to electric school buses. If you've been following along to part one of this Flipping the Switch on Electric School Bus series, you'll already know that it consists of two modules. Module 1 provided an introduction to the DOE's Vehicle Technologies Office Clean Cities Coalition Network, including how Clean Cities Coalitions can assist school districts in learning about electric school buses and provide technical assistance throughout the project. Module 2, which we're covering today, introduces electric school buses, including the current electric school bus market in the US, some pros and cons of adopting the technology, and key challenges to be aware of. So let's get started with Module 2 of the Electric School Bus Introduction. This is Electric Bus Basics and Key Challenges. Say that 3 times fast. All right, so starting with the basics. So what is an electric battery school bus or battery electric school bus, which is a BEB and is an all-electric bus that uses a battery pack to store the electrical energy that powers the drive motor. So BEB batteries are charged by plugging the bus into an electric power source. To learn more about basic information related to BEBs, such as vehicle types, kind of the general schematics of the types of vehicles, charging infrastructure, and other information, please explore the electricity, fuel, and vehicle section on the Alternative Fuels Data Center, where the link to the website is pictured here. And you'll just get more information on some of these key aspects and become more familiar with the different aspects of the technology. So let's start with kind of laying the groundwork on the population of BEVs, which has been growing across the nation, where the majority of the vehicles tend to serve in the transit industry today. So right now, there are close to about 3,000 BEVs in operation, which did experience a 24% growth increase over just the last year. So many fleet owners are considering BEVs for similar applications, and the National Renewable Energy Laboratory utilizes the data we have from the transit industry as baseline knowledge to support analysis of other applications, such as school buses, to help inform purchase-making decisions and transitioning to that newer technology. The growth of BEVs is expected to expand into other applications, such as school buses, where today's population is less than 1%, as diesel tends to dominate the majority, and there are some alternative fuel vehicles, such as propane and natural gas. To support this growth, there are multiple manufacturers that now offer electric school bus models, and they tend to meet the seating and range needs of existing fleets. Here's a list of available electric school buses from various OEMs and their associated model offerings that provide examples of the estimated range. Buses are available in Type A, C, and D for different school districts' requirements and their routes. Something to keep in mind, though, is that this range is an estimate mile maximum, and it will depend on other factors that we'll start to discuss shortly. So again, we encourage the use of the vehicle search tool on the Alternative Fuels Data Center for the most up-to-date information, and the website link is shown here at the bottom of the slide, because this technology is continuing to change and continuing to evolve. As with all emerging technology, there are multiple factors to consider when comparing to your baseline technology and trying to understand what impacts that change might bring. So here's a brief list of some pros and cons that transit fleets have experienced with electric buses this far as they've taken on newly adopted technology. So let's start with some of the benefits. You can see that a lot of fleets have experienced quieter operation and no tailpipe emission benefits. So it smells better, it's quieter, it's a little more pleasant to drive. There's some flexibility with the charging of your fleets if it works well within your operations, to where you can manage off-peak charging and potentially lower your electricity rate. I'll pass it over to Jesse later on for more details on that. Within that, it's kind of the flexibility on your charging agenda as well. So if midday charging works better and night charging, then you kind of have the benefit of switching between those, as well as where that centralized charging equipment is located based off of your needs and your routes. And the availability of chargers has been increasing as well as this technology tends to grow. Another key benefit that's been experienced is generally lower maintenance costs compared to the baseline technologies. And again, that's mostly diesel and then some propane and natural gas applications and some gas. Some of the cons when switching over technology is the initial higher capital costs. So the battery electric buses do tend to cost more at initial time of purchase than the baseline buses. And as with taking on new technology, you need to support that. So that will likely require added infrastructure. And then again, to keep in mind the efficiency, so where your fuel savings and some of your range maximums come into play, can be affected by different factors, such as your route characteristics, driving style, and other loads that are included or utilized on the bus during the route. So with that, it also may require a little bit of adjustment to the reconfiguration of routes to optimize and decrease some of those impacts on your efficiency. As with all new technology, there's also a learning curve, especially for your maintenance staff. And if you don't have the flexibility on managing your charging times, you may experience some increased rate charges during the day. And again, Jesse will get into that in more detail shortly. So let's start breaking down some of these cons and key challenges and how we can address them. So let's start with maintenance. Taking on new technology, some technicians lack basic EV knowledge right now. So it's important for them to understand the difference in architecture between an internal combustion engine and an electric vehicle now. So that would include basics of electric systems, high voltage safety, and then being able to troubleshoot those new issues that come along with EVs. There's also currently a small pool of trained technicians because, again, new technology. So we're just now starting to see those technicians enter into the learning and the workforce to support this. So there's need for more OEM trainings to support that need and increase the training of technicians. And that need is being recognized, but these training programs are just now starting to be developed. So again, we're at the start of the learning curve and just some things to be expected as your technicians take on that new challenge. Another key challenge that I mentioned earlier is how different factors will impact the efficiency of your battery electric bus. So a BEV efficiency is dependent on a few factors. Most notably is the propulsion and auxiliary loads. So propulsion efficiency is generally relatively consistent, although it could be somewhat impacted by passenger loading and operator driving style. In this example, and again, this is coming from some transit studies, we have a 2020 bus electrification study where the auxiliary load offset the BEV efficiency because it was consuming so much energy. So specifically in this case, the HVAC system dominated accessory use, which impacts operations in colder climates than others. So keeping it warm tend to use a lot of power, right? The auxiliary loads greatly increase the amount of energy consumed and decrease the overall efficiency of the BEV, which in turn increases the time required for the vehicle to charge at the end of the day. So you don't get as long of use out of your battery because that battery was supporting your HVAC, so you have to charge earlier, which means you're taking on the cost of charging a little earlier than expected. So those are a few key challenges related to maintenance and efficiency impacts. Now I'm going to pass it over to Jesse, where he's going to address some of those infrastructure challenges and how they can impact some of the costs as well.
All right, well, thanks, Lauren. And in terms of understanding different energy consumption for BEVs, under different operating efficiencies, they may use more or less energy, but regardless of how efficient they are, they're always going to need to recharge at the end of the day. And typically that's done through EVSE and or also known as electric vehicle supply equipment. And that's broken down into a couple of different types. Most commonly, you might be familiar with AC EVSE or AC charging that takes power from the grid in AC form and passes it directly to the vehicle. Whereas DC fast charging typically takes AC power from the grid and then it converts it to DC power before then passing it directly to the vehicle's battery. There's two different types of AC power that's very common. The lowest type of which is level 1 that requires 120 volts. Typically gives a battery electric bus around 1 to 5 miles of range per hour of charge, which is not quite that much energy when you're thinking about how much a bus would typically need for a daily period of charging. Now, compare that to DC fast charging, which is much more powerful and can give up to 40 to 80 miles of range in about 20 minutes. And that's quite a bit amount of power and actually likely much more than a bus might need in its overnight dwell period or opportunity for charge. And really looking at both of those considerations, the sweet spot in terms of power delivery is really level 2 charging that requires 240 volts of electricity and can give about 5 to 20 miles of range per hour of charge. It's a great sweet spot. It typically can refill a bus within a typical 8 to 10 hour dwell period, and it can provide up to 19 kilowatts of power. It's a really great option for most applications and is the simpler to install than DC fast chargers, but much quicker to charge than a level 1 station. And additional topics on power considerations and installation costs will be covered in later discussions. On the next slide here, we have a bit of a broken down of different electricity rate structure factors. And this can certainly be a key challenge for the adoption of some battery electric buses. And I definitely want to highlight a few key elements here. One being the utility grid demand, another one being sort of the base rates. And especially with commercial utility rates, there's more than just the energy charge. If you're paying your electricity bill at home, you might be used to something like a 10 to 12 cents per kilowatt hour energy charge. However, with a lot of commercial buildings, there's also what's referred to as a demand charge. And this is in addition to the energy charges. And it's really based upon the peak power consumed throughout a given billing period. So it doesn't really matter how much energy you're requiring over a month-long period, but what is that highest rate of power over the entire month that you consumed? And it then creates sort of this two-part rate structure system where there's both energy charges and demand charges. And therefore, you must also consider not only how much energy you're consuming, but what is your peak power at any given point. And that's really where it can potentially come into a factor when you're installing many different charging stations across a facility and really how the energy demands of those buses line up with facility loads. Think if you're charging all your buses overnight, they may not coincide with the facility loads and therefore won't be adding to that peak demand. However, if at the time whenever most of your buses are plugged in, you still have many people in the facility working and have lights on and computers running, it's likely that there might be a coincidence between those two loads, which could then increase the demand charges that your facility is seeing. On the next slide here, we have a bit of a comparison of how these different rate structures can have an impact on overall energy costs. And on the left side of the chart, we have a facility where in the beginning year or so of this analysis, there was a time of use rate structure where the energy charge actually changed throughout the day, and there were on-peak, mid-peak, and off-peak elements to this rate structure, where throughout the day, the energy cost actually varied based on the time of day and a schedule that was predetermined. And as you can see here, that each of those monthly energy charges was actually a breakdown of a series of on-peak, mid-peak, and off-peak energy consumption. And typically these on-peak are the most expensive portions of the rate structure, and they're generally in the late afternoon. And they don't typically coincide with the overnight dwell periods of many battery electric buses. So there's certainly the opportunity for battery electric buses to take advantage of those lower off-peak rates. And you can see that where, for the most part, that was a large portion of what this facility saw. However, in about January to February of 2016, the rate structure shifted to include what I was referring to as a demand charge. And therefore, as a result, you can see the energy charges from that time of use rate were slightly lower because of the incorporation of this demand charge. And you can see how that actually was a huge element of this facilities rate structure, and how much they paid for energy was highly dependent on that total peak demand, which may have only occurred for a short period of time throughout the month. And at that period, they may have been consuming somewhere in the range of 20 to 40 kilowatts. And for most of the rest of the month, it might have been on an average of 10 kilowatts. And when you have a peaky demand that has these large spikes at certain periods of the day, that presents a great opportunity to level your overall load profile and reduce those peaks, and then also mitigate those demand charges. Next slide here. We're finally, in terms of understanding those peak demands, it's a factor of how many EVSE you're installing, but in terms of planning for the infrastructure installation, you shouldn't only consider your utility rates, where yes, the total number of EVSE installed can have an impact on your utility rate structure, but you should also consider how many chargers will be required for how many buses you have. You may have buses that might not need to charge at the same time, and therefore the total number of chargers required could be less than the number of buses you have. If that is the case, you must take into account different charging logistics and how you'll be moving those buses around to take advantage of a smaller number of EVSE and charging stations. However, if you do maybe need a one-to-one ratio and all of your buses need to charge at the same time, you'll probably have a large number of EVSE, and therefore the placement of those chargers is very key to make sure you have the lowest cost installation requirements, and we'll get that in that a little detailed later on in the series. And then also, if you're maybe planning for future growth of BEBs, you have 5 right now, and maybe you want to plan for 10 or 15 in the future. Just because you're purchasing a set number of BEBs this year does not mean that's all you need to plan for in terms of your EVSE installations. There's a lot of expensive elements to installing charging infrastructure, and considering towards the future and planning ahead, especially when you need to trench through concrete and install conduit, it's best to do that all at once or mitigate how many times it's done at one site. So therefore, planning for the future and installing additional infrastructure when you have future electrification goals is really an important factor as well. So the next slide here, just to wrap up, there is, we're talking about BEV efficiency, which is highly variable. And as Lauren mentioned, there's quite a few different elements in there that can dictate how much energy is required for these buses. And then that energy, it comes from, is delivered through the utility, which has different rate structures and different concerns. So we mentioned time of use rates, energy charges, and demand charges. And really understanding that rate structure is really important to understand the impacts and requirements of energy needs for these buses and the cost to supply that energy over the long term. And then finally, make sure that, as Lauren mentioned, you're working with your maintenance team and you understand the maintenance requirements and how that training is going to be required to bring on this new technology. Thank you for joining us, and that concludes Module 2 of Part 1 of Flipping the Switch on Electric School Bus Series, an Introduction to Electric School Buses. Thank you for joining us, and we will have multiple parts coming out here in the future that cover a wide range of topics between working with utilities, charging infrastructure, vehicle requirements, in-use performance, driver training, as well as cost factors. Please join us next time for Working with Utilities, where we'll dive more into detail on rate structures. And until then, please feel free to jump on the AFDC for some more technical information on electricity basics and battery electric buses. Thank you.